The overall goal of this procedure is to fabricate a sharp polymeric microneedle array which may provide potential applications in the painless delivery of low molecular and macromolecular therapeutic agents through the skin. This is accomplished by first fabricating a photomask consisting of embedded microlenses via patterned isotropic etching. The second step is to fabricate microneedle shafts by placing the embedded photomask over a bath of pre-polymer solution and focusing UV light into the solution through the microlenses, polymerizing the exposed solution. The final step is to fabricate the backing layer to support the microneedle shafts. This is accomplished by placing the microneedles, pointy side up, into a plate, then adding a pre-polymer solution and polymerizing the solution with UV light. Ultimately, the characteristic properties of the microneedles, including length, diameter, and the apex angle, can be observed using a stereo microscope.
The main advantage of this technique over existing methods like micromolding is that it is faster, it is mold-free process, and it does not require the use of high temperature. This method can help answer key questions in microfabrications like use of microlens to modify the path of UV light and the polymerization process.
This technique can be used to fabricate polymeric microneedles, which are useful for transdermal drug delivery. Although we are only demonstrating how to fabricate blank microneedles, this technique can also be used to fabricate drug-laden microneedles.
Begin cleaning a 4-inch glass wafer by immersing it into a quartz tank filled with piranha solution for 20 minutes at 120 degrees Celsius. Then rinse the wafer in distilled water and dry it using compressed air. When finished in the E-beam evaporator, place the wafer into a spin coater setup and add 5 milliliters of a photoresist to the center of the wafer. Spin the wafer at 3000 RPMs for 30 seconds to produce a 2 micrometer thick photoresist layer. Next, pre-bake the photoresist on a hot plate at 100 degrees Celsius for 1.5 minutes. And then place the master photomask and wafer into the photomask aligner and expose the wafer. Once exposed, hard bake the photoresist at 120 degrees Celsius for 30 minutes on a hot plate. Then, etch the pattern into the glass wafer using a solution of chromium and gold etchants at room temperature for 1 hour. Place the etched glass wafer on a hot plate at 110 degrees Celsius and melt wax on the opposite side of the glass wafer so that the entire surface of the wafer is covered with wax. Temporarily bond the glass wafer to a dummy silicon wafer by placing a silicon wafer in contact with the glass wafer and pressing firmly to remove the excess wax. Next, prepare a 200 milliliter bath of 10 parts 49% hydrofluoric acid and 1 part 37% hydrochloric acid in a plastic container with a magnetic stirrer. Add the sample and etch the microlenses at a rate of 7 micrometers per minute for 8.5 minutes while stirring. When finished, clean the wafer using deionized water and dry it at room temperature. Once dry, place the wafer onto a hot plate preheated to 100 degrees Celsius for 15 seconds. Then, separate the glass wafer from the dummy silicon wafer. Place the glass wafer into an ultrasonic tank containing N-methyl-2-pyrrolidone at 80 degrees Celsius and use ultrasonication for 1 hour to remove the remaining wax, the photoresist, and the overhanging chromium and gold layers at the edges of the lenses. Stack glass slides on either side of a rectangular-shaped cavity to set the maximum height of the microneedles. Secure each layer of the glass slide by applying a thin layer of pre-polymer solution onto the glass slides in between each layer. When finished, irradiate the setup with a high-intensity ultraviolet light for 2 seconds to fix the slides into place. Next, position the photomask so that the chromium gold-coated surface is facing the interior of the cavity. Ensure that the sides of the cavity walls are not obscuring the lenses embedded in the photomask. Fill the cavity with the pre-polymer solution until the chromium gold-coated surface comes into contact with the solution without any visible bubbles. Then, place the setup into a UV curing station and place a radiometer next to the setup to measure the intensity of the UV light. Irradiate the setup with high-intensity UV light between 320 and 500 nanometers for 1 second at a distance of 3.5 centimeters from the UV source. Following UV exposure, remove the photomask with the array of microneedles and pour the excess prepolymer solution back into its original container for reuse. Quantify the length and tip diameter of the microneedles using a stereo microscope using standard techniques. With forceps, place the microneedles attached to the photomask into a well of a 24-well plate, needle side up. Add 300 to 400 microliters of the prepolymer solution into the well until the needles are submerged to the height of the desired backing layer. Next, irradiate the setup with high-intensity UV light measuring 15.1 watts per square centimeter from 10.5 centimeters away for a duration of 1 second. Once the backing layer has polymerized, separate the backing layer on the microneedle array from the photomask using a sharp blade. Then, quantify the length, tip diameter, and base diameter of the microneedles with the backing layer using a stereo microscope. The effective UV intensity on the microneedle length and tip diameter was studied by varying intensity of the UV light from 3.14 to 15.1 watts per square centimeter at a constant focal length and light source distance. It was found that the average microneedle length and tip diameter increased with increasing intensity. Shown here are the effects of 300 microliters versus 400 microliters of backing material on the overall length of the microneedles as well as the fracture force of the needles. As expected, with more backing material, the needles are shorter overall, but they also gain additional fracture force due to the extra support.
After watching this video, I hope you have a good understanding of how to fabricate polymeric microneedles.
Once mastered, this technique can be performed in 5 to 10 minutes if the procedure is performed carefully and the photomask is ready.
Please remember hazardous materials such as hydrofluoric acid and UV rays are used, so personal protection gear should be worn at all times.